So welcome back. Yesterday whatever we were discussing is about the diameter of the bubble, that how the diameter of bubble is being calculated, and what we have done, we have said that there are different forces which are critical, and those forces was buoyancy force, momentum flux of the gas, the surface tension force, drag force and inertial force. And we said that if we do the combined balance, we will get a diameter equation, that what will be the diameter of the bubble which will be formed, and it will be detached from the surface. Okay, and we have taken a simple C plate holes where the small holes were there, and that is going to be the function of the hole velocity, the flow rate, Weber number and surface tension and all. So all this we have done. We have also derived the formula for the simpler case where the buoyancy and surface tension is only playing a role, and the surface on this bubble size generated because of that. So if you see this formula whatever we have developed, if you see the first term, Weber number term, only the first term of this which will be multiplied by 1, so it will be the first term, that will be the only formula for the diameter of the bubble once only buoyancy and surface tension is playing a role. If all other forces are also playing the role, then you will have a different formula and which you can use to calculate the bubble diameter. Okay, and if you see this is a function of Weber number, and Weber number is defined as the ratio of inertial force to the surface tension force. Okay, and which is critical to determine the bubble diameter. Now several researchers have put their own correlation or different correlation to calculate the bubble diameter depending upon the different cases, the properties of the system or different type of the systems. So I am not going to discuss all those correlations, but what I am going to see, what I have discussed already is about the basics, how these correlations are derived. Now you can say that for certain systems some forces are important, some forces are not important, and you can modify the equation for the diameter of the bubble, but the basics remain same. The next question in the bubble column design, if you go for bubble column design or if you want to understand the bubble column, is what is the shape of the bubble. So what we have done, we have found that what will be the diameter of the bubble. As I said that I am interested in the mass transfer, I am interested in the heat transfer, I want to do the reaction. So I have to first see that what will be the shape of the bubble depending on my flow rate. Again I am quoting that I am not taking coalescence into the account. If the coalescence will take place, a bubble break will take place, this story may be little bit different, and you have to model the bubble size distribution and all. That can be done with the advanced model. I will give the glimpse of that, but if you have interest we can go and discuss, we can discuss it further. You can write it to me. This is the next problem, is the bubble shape, that what will be the shape of the bubble once it will be formed. So generally the bubble, 4 type of bubble shape is being reported in the literature, and the first shape is, if the bubble is very small in diameter, it will be spherical in nature. So you will see a very pretty much a spherical bubble. So if the bubble is small, you will see the spherical size bubble. But if you put more gas, then what will happen? Before detachment, bubble size will increase. Now once the bubble size will increase, it will go to elliptical bubble, and you see a ellipse nature. So this is elliptical bubble. Now if you further increase the velocity or the bubble size, it means the bubble size, what will happen? You will see the bubble which will be kind of elliptical, but the upper surface will be more towards the spherical, and the bottom surface you will see some elliptical portion. Okay, but it will not be perfectly ellipse. The upper top surface will start swelling up and it will be going towards the spherical shape. And if you further increase the velocity, then you will get that spherical cap bubble. It means this bottom will get flattened up, the bottom will go up, it will be flattened up, and the top will becomes more and more spherical. You will see this kind of a shape. Now this bubbles will start wobbling. Okay, while if you keep on increasing it, you will get the spherical cap bubble. So this is called spherical cap bubble. Spherical cap. Okay. So this kind of 4 type of bubble is being formed depending on that velocity and the orifice diameter which you use for the bubble gas injection. Now we know that if suppose the spherical bubble is forming, you can calculate the diameter of the bubble very simply, that it will be what? It will be the volume of the bubble you can calculate, and that will be pi by 6 dp cube, and if you know the volume of the bubble, you can calculate the diameter of the bubble. Now if suppose this is not spherical, then the problem comes that how you will define the size of the bubble, because suppose it is elliptical, then what you are going to do, how you are going to decide the size of the bubble. Now, the bubble size or bubble shape actually going to be different, and what we will decide based on the equivalent diameter. Okay. Now, equivalent diameter, how you will say that for elliptical thing, then you have to find the equivalent diameter based on that elliptical volume. So, we will take the volume of elliptical bubble and we will say that this should be equivalent to whatever the volume of the spherical bubble. So, this volume will be fitted in which diameter of a spherical bubble which have the same volume as the elliptical bubble. So, you have to do the volume balance, and based on that you can find it out the D correlation, that what will be the equivalent diameter, equivalent sphere diameter for the different shape bubble. So, we defined it that way. So, say for elliptical bubble, if this is the A, if the major axis is say A, and I am using the notation which you might have used widely in the mathematics classes. So, this is say A, and if this is B. Or let us make it the mathematics little bit simpler, let us say it is 2A and this is 2B. So, that from the axis it is A one side and from the axis the height is B. So, if it is 2A and 2B and I want to find it out for this elliptical bubble which major axis is 2A, the minor one is 2B, then what will be the diameter of the spherical bubble which will have an equivalent volume as of this elliptical bubble. So, to do that, this is a very simple mathematics. We know that volume of the bubble for the spherical bubble, that will be pi by 6, say dp cube. I will write it dpe cube, or say let us write it dbe. Let us give a notation which is dbe. It means the bubble volume diameter which is equivalent bubble diameter in terms of the spherical, if this volume is equal to the spherical bubble volume. So, I will write it dBE, and that will be equal to that what will be the volumetric of this ellipse. Now, this volume will be pi by 4 3 and then B into a square. So, that will be the volume of the ellipse, and that is equivalent to this volume. So, you can find it out what will be dBE. So, dBE if you calculate from this place, that will be what? dBE will be equal to this pi will be cancelled out, this 6. So, you will get 8 into B A square whole raised to the power 1 by 3. So, you will get this will be what will be the dBE for the elliptical bubble. Now, this dBE can be used further to do the calculation, because we know the calculation whatever we did the calculation till now in the multi-phase flow, we did it for the spherical particle. So, now you can use this dBE to and use your equations whatever we have discussed, the momentum equation, the continuity equations, and then you can solve these problems by using dBE to get that thus you can solve the momentum equation. So, that will make your life little bit easier, and that is why for all the bubbles we define it in this way, the diameter we define for this way, okay, in this way. Now, how it will be generated, what will be the diameter, that you will generate whatever I have said in the previous, but if suppose the bubble shape has generated, that diameter will be further modified and you have to use this kind of a dBE. This dBE can be used in your momentum equation, in your continuity equation if needed, or any other equation which we have discussed till now. So, you can use this to do the calculation. Okay. Similarly, you can do it for the other shape also. What you need to do, you have to just find the volume of that shape, and that should be equivalent to the equivalent volume of the sphere which represent the same volume. So, that is the way you calculate the dBE in this way. Now, for wobbling bubble or elliptical bubble, different people have given different kind of a correlation to calculate that what will be the dE, what will be the dBE. Why? Because it is difficult to measure the 2A and 2B. How you will measure that? So, what you need to do, if you want to measure the 2A and 2B, then you have to depend on measurement techniques. You have to take a high speed camera, you have to take the photograph of the bubbles and all. So, what people have done, people have tried to correlate it with for the different condition, different system, and many researcher has given different correlation to predict that what will be the dBE. Okay. And dBE, instead of dBE, they have defined it in a parameter, in another parameter for say elliptical bubble. They have the parameter they have defined is small e, and that small e is nothing but it is equal to B upon A. So, they have defined a parameter E which is B upon A, what is the smaller to the maximum angle. So, E value is going to be less than 1. So, this way they have defined that whatever the E value, they have tried to correlate this E value with the different correlation. Now, once you have this E value, what you can do, you can convert this in terms of the E. you can say that in terms of the E, and you can get the dBE correlation, that what will be the dBE correlation. So, suppose if you want to calculate in terms of the E, what you can do? You can replace say B with the E. If you do that, then B will be equal to E into A. So, if I replace it here, it will be dBE will be equal to 8 into A and cube. This will be A cube, and that will be multiplied by E 1 by 3. Now, sorry, whole raised to the power 1 by 3. Now, if I do that, then it will be dBE upon A will be equal to 2 E raised to the power 1 by 3. So, I can develop this correlation. So, now if I know this dBE upon A, if I know this E value, so people have what they have done, they have calculated this E value given the different correlation in terms of the E for the different flow rates, okay, for the different surface tension to the gravity to the surface tension ratio based on that, and they have for depending upon the different flow rate, different fluid property and all, this E value will keep on changing, and the correlation has been developed in which you can see that how the E will be correlated for the different systems. So, several such correlation is available, but most of those correlation again is being available in the form of E. Say if I want to find this E is equal to 1 upon C1 plus Ito's number raised to the power C2. So, most of this correlation is in this form, E is equal to 1 upon C1 plus E naught EO raised to the power C2. Now, this EO is what? It is Ito's number. So, this EO is Ito's number, and which is the ratio of gravitational to the surface tension force. So, this Ito's number is actually gives the ratio of gravitational force to surface tension force. Okay. That is going to determine that what will be the shape of the bubble. So, this correlation is there. Now, many researchers have used, most of this correlation has formed it in this way. The value of the constant C1 and C2 are the constant, depends on your system specific, and if you change your system, you change your property, you change your conditions, this value of C1 and C2 will change. But most of this correlation of the E is validated in this way for elliptical and wobbling bubbles. Okay. Now, what is the Ito's number? Actually, you correlate in terms of the Ito's number, and if you write the Ito's number for this case, it will be G d cube, and it will be rho of liquid minus rho of gas upon sigma. So, this is the way Ito's number is being defined. So, you can say that this is going to be the gravitational forces, what is the gravitational forces there, and what is going to be the your surface tension force. Okay. So, this is the ratio of this, and most of these correlation is being developed in this way. So, you can find that what will be the shape of the bubble, and if you find the shape, you can also find the E value. If you know the E value, you can find it the dBE value. Okay. So, all this correlation, all these things you can find it out. Okay. Now, this dBE can be used in the momentum equation or any other equation which you want to understand the flow. So, that is the way we discuss about the shape, and definitely there is mainly 4 type of shape is available, as I said, spherical, if the velocity is very less, bubble diameter is very less, most of the bubbles are spherical in nature if their diameter is very less. So, if the diameter is less, it will be spherical bubble, if you increase the diameter further, it will be elliptical. If you further increase the diameter or flow rate for which the diameter is increasing, the bottom portion will start shrinking, the top portion will be becomes like a sphere, and then further increased velocity you will see that a spherical cap bubble where the bottom will be flat and the top will be the spherical shape, spherical cap kind of a behavior. So, this kind of a 4 shape of the bubble is being formed. Now, next is what will be the bubble velocity, how to calculate the bubble velocity. Now, if I know the velocity, I know the diameter, I know the shape, I can calculate about the mass transfer, provided if I know the volume fraction. Okay. So, for volume fraction again several correlations are available, most of those correlation are empirically fitted correlation based on the experimental data. Again, I am not interested to do all those things here because that will be a dedicated work on the bubble column reactor. What we are trying to see is that how the basics force balance equations can be used to understand or to solve these kind of a reactor problem. So, in the bubble column again, if you want to find the velocity, then we know that how the velocity, if the bubble will move upward, once it will achieve its terminal velocity, then what will happen, that the forces acting on it will be equal. Now, what will be the forces acting on it? It will be buoyancy force, it will be gravity force, and it will be the drag force. They are going to be equal. Once they are going to be equal, the bubble will achieve its terminal velocity and it will rise with its terminal velocity, and that is going to happen because once the bubble will start, then after certain time it will achieve its terminal velocity. It will achieve where all the forces will be balanced, and then it will be achieving its terminal velocity. So, if you want to calculate that what will be the bubble terminal velocity, then what we can do again, we can use the force balance equation which we have done. We can say that drag will be equal to whatever the drag will be equal to the buoyancy minus the gravity, okay, because this bubble will be lifting upward. So, what will happening, that gravity will be going to be balanced with the drag and this, okay. So, drag and the buoyancy. So, in that case, if I write the equation, I will say that the drag force is going to be equal, and we calculated the drag force. So, drag and buoyancy will be equal, and once I say buoyancy and drag will be equal, I am taking the gravity in part of the buoyancy. So, if you do that, you can write it as a CD. The drag force equation is CD into area into rho into V square upon 2. So, that will be the bubble this, and then buoyancy will be pi by 6, or you can say pi by 6 d bubble cube, and that will be rho L minus rho G into G. So, that will be your overall the buoyancy force which will be acting, buoyancy of the this, because of that it will be this kind of forcing it. So, drag and buoyancy is going to be equal, the buoyancy will be pulling it upward, drag will be pulling it downward. Okay. So, in that way if you do it, then what will happen, that your this forces will be equal. So, if you do that, you can write it in terms of CD. If you know that area, what will be the area? If I am taking again a spherical bubble, the area, projected area will be pi by 4 dB square. This will be the rho of fluid, or it means it will be, if I am taking liquid, this will be rho of liquid into velocity of the bubble. Now, say if velocity of the bubble we are getting it the terminal velocity, so I will say VTB square, terminal velocity of the bubble, divided by 2, it will be pi by 6 dB cube into rho L minus rho G into G. So, you can simplify it further, we can write it in terms of the Reynolds number. So, if we try to write it in terms of the Reynolds number, so that we can easily do it, we can write it in the non-dimensional form. I can say that CD will be equal to, I am trying to write it in terms of the Reynolds number. So, this pi and this pi will be cancelled out, it will be this 4 dP and this dP will be cancelled out. So, you will get dB, okay. Then you will say rho L minus rho G, you will see G, and then it will be, once you will divide it, you will see that pi by 6 not D. So, this will be 6 and this will be rho into L, rho L. So, we will get something like this. Now, what we need to find, there will be this VT square also, VTB square. Now, this 2 will be also multiplied, so this will be the 2. So, you will get this kind of equation for the CD which we have already developed. So, if you see that CD will be equal to this 2, pi will be cancelled out, dB cube it will go out, so it will be only dB. So, this will be 4 into 2, 8, then it will be dB rho L minus rho G into G upon rho L into VT square. Now, we can write it in terms of the Reynolds number. If you want to write it in terms of the Reynolds number, what we have to do? We know that what is Reynolds number? I have to multiply it here by, it is V square. So, I want to write it in terms of the Reynolds number, a square function, so that my velocity will be accommodated. So, what I am going to do, if I want to write it in this way, I will write it dB square, I will multiply up, dB square down, I will multiply 1 rho L up, I am multiplying with 1 rho L up and 1 rho L up, 1 rho L down. So, what will happen? Now, this equation will be 8 into dB cube rho L minus rho G into rho L upon 6 rho L square, rho L square into VTB square into dB square. Now, what we need? We need mu square up, and then 1 mu square will be multiplied with the down. Now, if you see this is what? This is nothing but Reynolds number. So, I can write this equation as CD will be equal to 8 upon 6, 8, dB cube rho L minus rho G into rho L into G upon you say mu square 6 into mu square, and then this value you can write it as mu square upon rho L square into dB square into VTB square. Now, this function is nothing but 1 upon Reynolds number square. So, I can write it as 8 upon 6, this will be 8 upon 6 dB cube rho L minus rho G into rho L into G upon mu square, and this will be 1 upon Reynolds number square. So, we will find the Reynolds number, and because this is based on that, so I will say Reynolds number of the bubble. So, bubble Reynolds number square. So, this is bubble Reynolds number. Now, this function whatever we are saying that this is nothing but or called Archimedes number. So, this function is called as Archimedes number, and this will be, if you write it here, then it is 8 by 6 or you write 4 by 3 better. So, you will write 4 by 3 Archimedes number upon Reynolds number square, Reynolds number of bubble square, that will be the CD value. Now, Archimedes number, this is nothing but Archimedes number and which define the motion of the fluid basically due to the density difference. So, this is the Archimedes number defines the motion of the fluid due to density difference. So, why the bubble is rising? Bubble is rising mainly because of buoyancy, and the buoyancy is being generated mainly because of the density difference. So, Archimedes number shows that the motion of the fluid or motion of the bubble, because of the density difference, it is being characterized by the Archimedes number, and the Archimedes number is being defined by this value, which is dB cube rho L minus rho G into rho L G upon mu square. So, that is nothing but the Archimedes number, and Archimedes number actually characterize the motion of the fluid due to density difference. So, if I do the force balance again, I will get the correlation between CD and ARE. Now what? If you want to find the bubble terminal velocity, you have the formula available, that what will be the bubble terminal velocity. Now the only question is, what will be the value of CD? Now again, we have discussed several correlation while discussing the drag force. You can use depending upon the system, depending upon what is your Reynolds number. As we discussed that several correlation is there, we are valid for a particular range, you can find the CD value. Now, most important or most oftenly used or widely used correlation for the CD for the bubble column is Shiller-Neumann, which is 1 upon 16 upon RE into 0.15 into RE raised to the power 0.687. This is nothing but the Shiller-Neumann equation. So, Shiller-Neumann equation is being used widely to do this CD. Now, if you have the CD, you can correlate it, you can find it out the bubble velocity. It will be also the function of Reynolds number, you can get the bubble velocity. So, Archimedes number, if you see the Archimedes number, if you know the bubble diameter, if you know the system, you know the system viscosity, you know the density of the liquid, you know the density of the gas, and if you can calculate that what will be the dB, what will be your bubble diameter, then what will happen? Archimedes number will be calculated. Now, bubble diameter will be fixed. The moment you fix your distributor plate, your gas velocity, we have already discussed that how to calculate the bubble diameter. We have already discussed that how dB will be modified if the bubble diameter is of different shape. You can do that, you can calculate the dB. If you know the dB, you can calculate the Archimedes number. If you know the Archimedes number, ideally speaking, you can calculate the terminal velocity of the bubble. So, you will also get that what will be the bubble terminal velocity. And if you get all this phenomenon, you can actually model all the things, you can understand that how the velocity of the bubble is there, what will be the velocity of the bubble, you can develop the correlation for the mass transfer, for the heat transfer and all, and you can analyze the system. So, this is the basic force balance we are doing. Again, we have neglected many of the part, like we have not included the shear that which will be caused and which may change the bubble shape. bubble size. We have neglected that if the bubbles are having coalescence or they are changing the shape over the time, or if they are having the coalescence, they are forming a bigger bubble, they break into the smaller bubble. We have not taken into the account any distribution, the bubble breadth or bubble generation, or any shear migration, or any because of the shear or any other forces, the breakage of the bubble. All those things we have not generated, we have not done, because if you do that, then you cannot solve it the analytical solution. And I said in the beginning itself that the motivation of all this course is to have an analytical solution, a simpler solution to analyze the flow. If you want to have a kind of a detailed solution, whatever I said, then we have to go for the numerical modeling approach, which we have already discussed in the previous cases. So this is all about the bubble column force balances. Now, as I said that different type shape of the bubble is being formed, different regimes is being there, and because of the bubble coalescence, bubble death and all, the typical flow structure, there are several flow structures has been found in the bubble column. Now, different flow structures depend again on the column geometry, column dimensions, your velocities, properties of the fluids, all this actually play a role in determining these structures. Now, these are the two graphs where the Diaz et al. In 2006 and 2008, and followed by some of my own work which we have published in as a thesis and some in chemical engineering science paper, we have observed that there is different regimes you can get, different kind of flow structures you can get, and that flow structure in 2D column, this is for the 2D column, and I will not say it 2D column, I will say it a rectangular column. So, in rectangular column, these are the flow regimes is being observed, that if your velocity, if you are increasing on this side, what will happen if your low velocity is there, low H by W ratio means height to width ratio of the liquid, say this is the width and this is the height of the liquid inside. So, if the height to width ratio is low, say around 1, you get that what happen if you inject the plume, you will see a single plume which moves towards one wall. If you have higher velocity for H by D ratio 1, H by W ratio less than 1, then you will see what will happen, that whatever the gas you will inject, it will form like a jet and it will move outside. If you have even higher height, then what will happen, you see the unstructured behavior and you observe certain plume. So, if suppose the height of the liquid is there and you inject the bubbles or inject the gas, it forms certain a plume. You will see this snake kind of a plume behavior is there. So, these works are being done, again these are the detailed analysis of the bubble column, but I am just trying to show you that the regimes are there in the bubble column. Even if you operate the bubble column, there are different regimes, and that regimes actually, again if you see these things, it is going in the rectangular column, it is going to be the function of the dimensions of the column, of the liquid height inside the column, it is going to be the function of the velocity at which you are operating the column. Okay? And if you make it inclined or something, it will be also the function of inclination. Similarly, Chen et al. And Lin et al. In 1994 and 1996 has given the dynamic macroscopic structure, and they said that there are different structures are being formed, and if you want to analyze those structures, you cannot use a single model which can predict all the structure or which can cover all the structure, and the multi-scale nature of the bubble column has been showed. It means you have to use the different scale model, or you have to use the model which can be used at the different length scales, which can predict at different length scale, or which is accurate or equally valid at different length scale, then only you can found all the structures inside. So, this is about the glimpse of the bubble column, whatever is available in industry. You can do the simple calculations if you want to find that what will be the shape of the bubble, what will be the velocity, terminal velocity of the bubble, what will be the diameter of the bubble, or you can have a numerical methods where you can have a detailed analysis. So, you can do the simple force balance and you will get a clear cut idea, or not even the very clear cut idea, but at least you will get a fair idea that how your system is going to behave, what will be the bubble size. At least the bubble size you will calculate, definitely it will be very close to the mean bubble size which will be found in your system. So, what will be the bubble size, what will be the diameter of the bubble, or what will be the bubble size, what type of shape you will get. If you are getting this shape, how the bubble diameter will change, what will be the velocity of the bubble which you will, through which it will be moving upward. So, different correlations is also being developed. Again, I am saying that while telling the velocities, this you can find the velocity here. Different researcher have given different correlation. Lot of correlation is there. One of the important correlation which I missed here is actually given by the Clift and Grace, to find that what will be the bubble rise velocity, and they said that bubble rise velocity UBR, which is the bubble rise velocity, it will be equal to 0.711 under root of G into dB, where dB is the bubble diameter and G is the gravitational fault. So, this will be there. So, similarly, lot of people have done different correlation has been developed. You can calculate the bubble rise velocity, you can find the, if you know the bubble rise velocity, you can find that what will be the residence time inside, that will be kind of, it can be discussed. You can, if you know the bubble just now, you can calculate the Reynolds number, you can use your mass transfer equations to calculate that mass transfer whatever it is happening. You can use the film theory, you can use the penetration theory, you can use the surface renewal theory, all those theories whatever you feel is valid or is valid for your case, you can do that. You can do the analysis of the bubble column, you can see that how much reaction is going to happen, what will be the conversion, what will be the residence time. So, all those studies can be done. Similarly, the another class of the bubble column you can say is airlift reactor. Now, this is again a gas liquid system. What we do, we give the guided path to the gas. So, what we put some downer, one riser and downer on this. So, we put some draft tube, these are the draft tubes, okay. Sorry, this is the draft tube and this is the draft tube, and what we happen, we inject the bubbles or we inject the air only under the riser section. Why we call it riser? Because here the bubble is moving upward and with the bubble liquid will also move upward. Now, what will happen on the disengagement section, the bubble will go outside of the system, while the liquid which is coming here, because most of the bubble is coming from this place, on this place the liquid will have only one path to go down from this place, which is called downer, and again it will come back and do the riser. So, you get a directed flow. This kind of a system is widely used. There are different geometries possible. The riser can be center of the column, the riser can be near the wall, or it can be on the one side, it can be riser, other side can be downer. So, different type of structures are available. These kind of flow reactors are widely used for the biological application, wastewater treatment, or any algae kind of a generation of biological application. This kind of airlift reactors are widely used. All the principles are going to remain same, the force balances are going to remain same as we have discussed earlier, okay. The only thing will be the structure will be different, and if you want to solve the 3-dimensional simulations the way we did the modeling, then the models will be little bit different, the flow profiles will be different. But the basic force balance for the bubble size, for the bubble velocity, for the shape, these are going to be the same as whatever we have discussed till now. So, with this gas liquids column or gas liquid systems we have covered, which is the main class is the bubble column and airlift reactor, okay. So, I am not going to discuss airlift reactor in detail. If you have any problem or if you have certain interest, please write to me on forum and we will try to discuss it further, okay, but that will be the offline discussion. So, with this what we will move now towards the gas solid reactors. So, gas liquid reactor we have already covered. The next class of the reaction or next class of the reactor is gas solid reactor. Now, in the gas solid reactor actually there are different type of reactor available. Now, those are packed bed reactor is one of them, then fluidized bed reactor. Actually, before fluidized bed there will be one more thing will come, which is called trickle bed, but that is mostly trickle bed are gas liquid solid. Most of the time it is being operated as a gas liquid solid, not most of the time the trickle bed reactors are gas liquid solid reactor. Then fluidized bed reactor, then fluidized bed has a certain class, now it can be bubbling fluidized bed. Okay, it can be turbulent fluidized bed. Fluidized, or it can be circulating fluidized bed. There are several other class, we will discuss about the regimes, but mainly this is divided in this 3 part: bubbling, turbulent and the circulating fluidized bed. So, what we are going to do now, we are going to discuss briefly about all these beds. We will discuss mainly about the packed bed. Trickle bed is approximately same. Again, all the force balance will be going to be the same. Only the liquid part will be increased. Then we will discuss about the fluidized bed, and in the fluidized bed we will try to discuss mainly about the bubbling bed and briefly about the circulating fluidized bed. Again, we will try to see some force balances here. So let us start with the packed bed. I will briefly cover it. Most of you might have done it thoroughly, but I just want to show that how the force balances which we have learned can be used to do the force balance in the packed bed and to derive the sum of the equations which is widely used in the packed bed reactor. So now what is packed bed or fixed bed? It is also referred as a fixed bed. What we do, we dump the solids inside the column, inside the reactor. Say this is my reactor vessel. We dump the solid, though I showed a very systematic bed, but generally the bed is not being that much symmetric. You dump the solids and it forms a certain shape inside. The only thing is you operate it at a velocity that the bed will not move. It is lower than the fluidization velocity or minimum fluidization velocity. So, solid will be in the packed form. Okay. And it means what? It will be packed and they will not move in the time frame of reference. So, if you talk about with the time, the particle movement will be 0. They will not be moving. So, that this kind of a bed where the particle is being dumped or catalysts are being dumped and they held at a certain place and their place or their position does not change with the time, it is called as a packed bed. So, the position of the solid, they move certain things, but not much. Position of the solid, they can vibrate, but they cannot move. Solid change with the time. So, such frame of reference is called packed bed reactors. Now, this is one of the simplest gas solid reactor, okay, very simple. The advantage is low maintenance, low cost because there is nothing available here, okay. So, this is all is there. The only problem is the heat management. The problem is temperature management or heat management. Flash control. So, this is the only problem. Neither generally these reactors are very calm, very simple. What you need to do, very simple to operate also, and there is no maintenance cost almost, only the cost of the catalyst you need to change, but the column wise, the reactor wise, there will be no maintenance, it will be available. So, it is very low cost because you just have to dump the solid inside. You take a vessel, you dump the solid inside, you pass the gas or the liquid, you can pass the gas or liquid, and you have to maintain it in such a way that the particle does not fluidize. Okay. So, you have to maintain a velocity which is lower than the minimum fluidization velocity. The only drawback of this column is you have a very high pressure drop. The pressure drop will increase, and if you keep on increasing the bed length or bed height, the pressure drop will be very high. So, what is the basic question which you have to encounter once you are designing a packed bed reactor is that what will be the pressure drop or what will be the pump specification or blower specification or compressor specification you need to pass the fluid or pass the gas from this packed bed. So, you have to give that much delta P, that should be operated at that delta P or that pressure, then only the gas will pass through this bed. So, that is the only question is being asked, or you should understand that this much is the pressure requirement is there. So, the delta P calculation in the packed bed is the major critical parameter. Okay. The bed has several advantages I discussed, very simple geometry, low cost, low maintenance. Okay. It performs well only for very highly exothermic reaction or endothermic reaction, whether the heat evolve from the system or you supply the heat from outside of the system, you are supplying the energy from the outside. What happens if the diameter of the column is very big, then you will not see the proper temperature balance. So, you will see the temperature gradient across the radial and across the axis also if you are supplying the temperature or hot air or something, hot fluid. So, you will see the temperature gradient, the temperature maintenance or temperature management of the bed is not that good. temperature control of the bed is not that good, and in case of very fast reaction, a very highly exothermic reaction, you see some hot spot formation and it may also cause a runaway reaction. So, these are the basic drawback of the packed bed reactors, but the major advantage is it is simple. You have to just dump the solid and then forget about it, your job will be done. So, it is very easy to operate, very easy to handle, very easy to maintenance, and it is low cost. And that is why that given a choice, if I have a choice, I would never like to operate a fluidized bed. I will always try to go with the packed bed. The fluidized bed we operate, and we will discuss about the fluidized bed once the conditions are such that we cannot live with a packed bed reactor. Okay. In the packed bed, the calculations are very simple. You just need to have one question in your mind, that what will be the pressure drop needed to force the fluid through the bed, and based on that pressure drop calculation, you can calculate that what will be the pump specification or compressor specification or blower specification you require. So, what we are going to do, we are going to see that what will be the force balance. So, suppose this is a bed and certain solids are dumped inside of the bed. Assume it there is some, you are seeing some pores. So, the solids are being dumped, they are being kept inside. Now, let us assume that the height of the bed is say LB, this is the length of the bed, and the area is A, capital A is the area of this, or you can say the diameter. I am writing in terms of the area because the area will be cancelled out all the time, and this is the superficial velocity, which is say U naught, which will be the superficial velocity of the gas which is going inside the reactor. So, what we need to do, we need to calculate that what would be the delta P. Now, let us assume that we have already done that delta P calculation in the beginning of this multi-phase flow courses, and I will take you a little bit back, and we have also discussed it in this course, that for single phase flow how you will calculate what will be the delta P equation. We have already done that. Okay, we have seen that you can solve the Navier-Stokes equation or Bernoulli equation and you can derive the delta P. So, the delta P equation for the single phase flow, where the flow is taking place in a pipe, is being kind of derived, and that equation, if you remember, this delta P will be equal to 4, delta P upon rho will be equal to 4 F, which will be friction factor, L V square upon 2, this will be divided by D. So, this is the delta P equation, where F is the fanning friction factor. So, you will get this equation. Now, this equation again can be modified. Actually, you can see that how to calculate. So, you know the delta P in a pipeline. So, this is the equation only if the single pipeline is there, one pipeline is there, empty pipeline where the fluid is passing. So, what will be the delta P of the fluid? You can calculate it with this equation. I do not want to derive this equation, we have done already in the earlier class, you can do it. Okay. So, this will be the equation we use for the delta P, okay, delta P upon rho. So, I can write the equation for delta P. So, delta P equal to 4 F into rho. Now, rho of fluid, or I said that, say I will write it in terms of the fluid. Why? Because it can be gas or it can be liquid, the basic force balance equation remains same. It will be L upon D into V square. Okay. Now, that is what is the pressure drop in a pipeline where there is no solid present. Now, if there is a solid present, what will happen? Your path, the pressure drop equation will be modified. Why the pressure drop equation will be modified? Because now the gases or the liquid, whatever you will flow across it or whatever you will pump or push through this bed, will go through the path available or the fraction path available between the solids. So, suppose this is the path available, it will go through this, it will never go through the solids, okay, till the solids are not porous. Assume that solids are non-porous, it will not pass through the solids. So, it will go through the path which is available after the packing of the solids. So, which is the tortuous path is there, or the wide fraction which is present within the solids. So, it will go through that, and because of that what will happen, your equation will get modified. Now, how the equation will get modified, we will try to see that. So, coming back to this equation, what we are going to do, we are going to take the delta P in the empty column and then we will pack it with the solids and we will see that how this equation will be modified. Now, we know that this equation, actually the friction factor is a major problem, that what will be the friction factor, and this friction factor is a function of Reynolds number, and we know that if the F Reynolds number is laminar or this flow is laminar, I will say not, I will not write the Reynolds number because that is valid only for spherical pipe. I say that if flow is laminar, then F is equal to 16 upon Re, Reynolds number. and Re is nothing but 16 upon V into rho of the fluid into d upon mu of the fluid, okay, and this is the diameter of the pipe. So, I can modify this equation, and this equation will be 32 into mu of fluid into V into L upon d square, okay, into rho of fluid. Okay. So, that will be, it will be modified. Now, rho of fluid will be cancelled out, actually rho of fluid is here also. So, this rho of fluid will be cancelled out. So, you can say that this will be the delta P equation, okay. This will be the delta P equation. Now, what we need? We need to know that what is the diameter, what is the diameter. Now, the diameter will not be the diameter of the system, because you are going to have a void, okay. So, the exact diameter is not the diameter of the system. Exact diameter will be the fraction where the voids are present, wherever the void is there. So, you need to find this d value, and you need to see that what will be this v value. Earlier we can take a superficial velocity because the column was empty, okay. So, we work on the superficial velocity, okay. But now, what will be the value of v, what will be the value of d? That is the major question. If you understand that, we can calculate that what will be the pressure drop through the packed bed for laminar flow condition. Now, we know that we have already derived it, that what will be the correlation between the velocity inside and superficial velocity. So, we have already developed that correlation, we have discussed it. So, inside velocity, say u will be equal to u naught upon epsilon, where epsilon is the void fraction. So, what you can do, how you have derived it? You can do it with the continuity. So, continuity says that mass in is going to be the mass, whatever the mass is going to be balanced at two different layers. So, if you take at any place inside this, what will be happening, that u naught, whatever the mass going is rho of fluid into u naught into area, and that will be equal to rho of fluid, that is into u into your area, and area will be now multiplied with the volume fraction. So, that you know that whatever the flow area is available. So, if you do that, area will be cancelled out, rho will be cancelled out, you will get this value. It means, if I write it, I will say this will be u into void fraction into area into rho of fluid. That will be equal to rho of fluid into u naught into area. Now, you know that rho f and rho f is cancelled out, overall area is same. So, you will get u will be equal to u naught upon epsilon. We have already done that, just to revise it again. So, you will get this u value. So, we already know the u value now. Now, what is about the dp? What is about the diameter of the column? So, this v will be modified with this value. So, what will happen? Your equation will be changed. I will just put it here. So, it will be 32 mu of fluid, it will be u naught into length. Now, length will be the length of the bed. So, I will replace it with the LB upon d square into rho of fluid. So, this will be into rho of fluid. So, that is the way it will be modified, this equation will be modified. Now, what we are going to do, we are going to put it here, that how this things will be modified. I think rho will not be there, I just forget to cut the rho, because this will be rho, delta P will be equal to rho f, and if you write it in terms of the Reynolds number, this will be 16 upon V rho and f, and this rho will be cancelled out actually. So, it will be only d. I just did it. So, please do this, you will find it out. This will 4 f rho f L d upon V square. If you will write it 16 upon V rho d upon mu f, if you do it here, then what will happen? This 2 and this 2 will be cancelled out. This will be V square upon 2 also. So, this 2 and this will be cancelled out. This will be 2. Now, if you put it here, like let me do it actually. So, delta P will be equal to 32. This will be mu f into rho f into L V square upon d. Now, Reynolds number I am writing it in terms of the V rho of f into d. So, V rho of f into d into mu, this rho f will be cancelled out, V this will be cancelled out, this will be d square. So, what you will get 32 mu f into V into L upon d square. So, that is what you will get. So, now you will get this equation and this will be divided by epsilon. So, this will be the delta P equation. Now, what you need? You need that what will be the diameter, because diameter is not going to change. So, we know that in case the diameter is not regular, what we need to do? We define a term which is called equivalent diameter. Now, equivalent diameter is being defined, or hydraulic diameter or equivalent diameter or hydraulic radius. It is being defined as dH. So, the hydraulic radius or hydraulic diameter is 4 times of the cross sectional area by weighted parameter. Okay. So, 4 times cross sectional area by weighted perimeter. Now, if I am talking about the cylindrical column, what we need to do? We need to find it in terms of the volume. So, I will multiply by the length top and bottom. If I just multiply with the length, which is going to be the same. So, that is the length. If I multiply it, it will be say LB, LB. If I am multiplying, this will be 4 into volume of reactor or volume of flow volume available divided by weighted surface area. So, volume of flow into 4 divided by weighted surface area. Now, what we need to do? We know that what we need to find it out, that what will be the volume of the flow. So, volume of the flow will be what? We know that what is the volume of this reactor, that is, if suppose this is there. So, volume of this reactor will be area 4 cross area into length, say LB, that will be the volume, but volume available for the flow will be only the void portion. So, we will multiply with the epsilon, which will say that what is the void fraction available. So, volume of flow or volume available for the flow, I will write it in this way for more clarity. You can say volume available for flow of fluid. So, this will be this. Now, area will be what? That will be the weighted area. Now, that weighted area will be what? That will be across the particle fraction, that what will be the surface to volume ratio of the particle. So, that area will be defined as your length we have already multiplied up and down. So, that will be 1 minus epsilon, and this area will be defined as area surface to area of this whatever the surface to particle volume ratio. So, that will be the A. Small a, I am defining it as the surface to volume ratio of the particle, and because you are multiplying with the volume of the particle, you have to multiply with the volume. It will be multiplied by capital A into LB, where A is surface to volume ratio of the particle. Ratio of particle. So, what we are doing? We have to find the weighted area, that what will be the weighted area. So, weighted area will be the area which will be weighted. So, this particle is there between these two particles, say this is the flow. So, fluid will pass through say this line. Now, if fluid will pass through this line, what will happen? That this areas are the weighted area. So, for that what you need to find, that what is the surface to volume ratio of the particle, and then that will be multiplied with the volume of the reactor whatever is available into 1 minus epsilon. Why 1 minus epsilon? Because 1 minus epsilon is the solid fraction. So, that will give you that what will be the weighted perimeter or what will be the weighted area. That will be the all the solids which will be weighted, not only the walls, but the solids will be also be weighted. That will be the weighted area. So, in that way we write it in this way. Now, this small a is surface to volume ratio of the particle. Now, surface to volume ratio for say if the particle is spherical, the surface area of the particle is 4 pi into d square. So, 4 pi r square you can say, and the diameter this way particle is 4 upon 3 pi r cube, where r is the diameter of the solid. So, if you do that, what will happen? This 4 pi will be cancelled out. It will be what? It will be 3 upon r, or you can write it 3 upon diameter of the particle. So, I am writing dp, which is the dia of the particle. And it will not be 3 because you are converting r to dp, it will be 6. So, the a will be 6 upon dp. Now, what will happen? You can replace this a value here and you can calculate the dh. So, now the dh will be, I will just modify the dh here again. So, if the dh I will say a and lb will be cancelled out, it will be 4 epsilon upon 1 minus epsilon into a. So, this will be 4 into epsilon upon 1 minus epsilon into a, and a is what? It is 6 upon dp. So, this will be 6 upon dp. So, it means you can write it as 4 upon 6 epsilon upon 1 minus epsilon into dP, that will be the dH value. So now again I can do this dH value, I can put it here, and here d will be what? It will be dH, because I will take the hydraulic diameter instead of the pipe diameter. This will be again modified, delta P will be equal to 32, it will be mu of fluid, it will be the length of U naught LB, U naught into LB upon dH square into epsilon. Now this dH square will be replaced here, you will write it out dH square, so this will be 32. Now you can cancel it out, it will be 2 upon 3 again. You can write here mu f into U naught into LB upon epsilon, this epsilon we can say right here. Now I am doing dH square on the separate side, if you do that it will be epsilon square 4, it will be into 9, and then this will be 4 into 9 upon 1 minus epsilon square into dP square, into dP square. So you will get this value. Now if you solve this, then this will be again further solved, this will be 8, so this will be 972. So you will get 72 mu f U naught into LB upon dP square into 1 minus epsilon square upon epsilon cube. This will be the delta P. Okay. This will be the delta P value, which will be mu f U naught L LB, which is the length of the bed, dP square 1 minus epsilon square upon epsilon cube. That will be this. So this is the delta P in the packed bed for the laminar flow. Now experimentally it has been observed that this equation, actually the constant is not 72, but it is 150. That is the experimental observation. Why it is the more? Because we are taking the straight path, we have not taken the tortuous nature. Actually, if you see this bubble column, the path is not straight, there is a tortuous nature of this path, and we have simplified that while doing our this force balance calculation. And because of that, the constant value get modified, and instead of 72, we found that more resistance is there, and that is why delta P will be higher because of the tortuous path. So this 72 is being replaced with 150. And that has been found experimentally. So this is 150, and again I am telling why it is 150. Don't worry, all the force balance is correct. We have not taken the tortuous path into the account, and that's why it is coming 150. So this is there, and that is a class of the equation which is being used to calculate the delta P in a packed bed for the laminar flow. So this is for the laminar flow. Now we know that the laminar flow concept for the particle flow, when the particle is there, this is equation has been found to be experimentally valid till the REP, Reynolds number of the particle, is less than 10. And the equation is very famous equation, and it is known as Kozny-Kármán equation. Kozny-Kármán equation, which is valid for laminar flow of the packed bed reactor. Similarly, what we can do, we can derive the equation for the turbulent flow. Now, if I divide the equation for the turbulent flow, we can do it very quickly, you can also do it. So, that will be again delta P upon rho is what will be equal to 4 F rho of fluid into L upon D into V square upon 2. Now, V we have already defined, that is U naught upon epsilon. So, we can say that this will be 4 into F L upon D into U naught square upon epsilon square into 2, and D will be equal to what? DH. So, you can replace this DH value from there, whatever the way we have defined, and DH is what? DH will be equal to 2 upon 3 epsilon upon 1 minus epsilon into dP. So, you can use this. So, this will be DH will be replaced, this will be 4 F L U naught square upon say 2 into epsilon square. Now, DH I am again replacing with this, it will be 2 into 3, this will be multiplied by say 3 into 2, then into it will be epsilon to 1 minus epsilon upon dP. If you simplify it, then this 4 will be cancelled out, you will get 3 F L U naught square into upon dP into 1 minus epsilon upon epsilon raised to power 3. That will be delta P upon rho. Now, if you want delta P, you can also multiply it with the rho of fluid. So, you will get this value, and this is for the turbulent flow, and that is valid for REP greater than 1000. So, this is for the turbulent flow, you can say, and what you need to find the value of f. Now, depending on the value of f, it has been found that for Reynolds number f, this value is 3 into f is being replaced with 1.75 rho into u naught square into L of bed, this will be the L of bed everywhere, L of bed upon dp into 1 minus epsilon upon epsilon cube, that is delta p. And that's again the experimental observation, 3f is being replaced with 1.75, and this is valid for the turbulent flow. Reynolds number of particle is more than 1000, and again this is a class of equation which is called Brooke-Plummer equation. Plummer equation, which says that delta p in the turbulent flow. Then there is another class which is being there. So, this equations, if you will see, is valid for the two different zone, two different region. One is for Reynolds number less than 10, for Reynolds number greater than 1000. So, Ergun equation is there. A scientist Ergun, what he did, he added both the equation together and say that if you have to calculate the delta p in a packed bed, that will be the combination of Cronje-Kármán and Brooke-Plummer equation. So, it will be what? It will be 150 into mu into u naught into LB 1 minus epsilon upon dp square into epsilon cube plus 1.75 into rho into u naught square into LB into 1 minus epsilon upon dp into epsilon cube. And this is called Ergun equation, which is used to calculate the delta p in a packed bed, and it has been derived from the basic force balance equation, the way we have done. So, if you know this delta p, what you can do, you can calculate that. Now, you know that what is the delta p is there. Now, you can calculate that delta p, you can use the Bernoulli equation, you can calculate that what will be the power required for the pump. So, you can find it out the pump power, you can find it out the compressor power or blower power, whatever you are using in the flow. So, this is the basic force balance we do in the packed bed reactor. Again, this reactor is widely used for many application. The only drawback of this reactor is the temperature management and higher delta p. So, next time what we are going to do, we will discuss about the fluidized bed reactor. Thank you.